First century Alexandria. The greatest library on earth stands within sight of the harbor. And in a workshop somewhere in its shadow, a man named Heron fills a hollow bronze sphere with water, seals it, and sets it over a flame. The water boils. Steam rushes through two bent tubes, and the sphere begins to turn. Faster, faster, until it is spinning so fast the bronze blurs and the flame beneath it flickers in the draft. Heron has just turned heat into motion. He has built an engine powered by steam. The year is sometime around 60 or 70 AD. The Industrial Revolution, the moment when humanity will finally, properly harness steam to drive machines and reshape civilization, is 1700 years away. And Heron has no idea what he has done. This is the story of the steam engine that arrived too soon, and the mystery of why genius, alone, is never enough. To understand Heron, you have to understand Alexandria. This is not Athens, the city of philosophers debating in marble halls. This is a Roman port where three continents meet, where grain ships and glassblowers and metallurgists from across the known world collide. And at its heart sits something no other city has. The museum. Not a museum in our sense, a working research institute, funded by the Ptolemaic kings and then by Rome, attached to the Library of Alexandria. Mathematicians, astronomers, physicians, and engineers. Heron of Alexandria was one of them. We know almost nothing about his life. No birth date, no death date, not even a confirmed portrait. What we have are his books, at least 13 treatises, covering everything from geometry to mechanics to siege warfare. And buried in those pages is a blueprint for the future, written 17 centuries early. His most famous work is called Pneumatica, a manual of machines driven by air pressure and steam. But he was not the first. A century earlier, another Alexandrian engineer named Ctesibius had pioneered the science of pneumatics, compressed air. He built force pumps for fighting fires, water organs that played music by pushing air through pipes, and clocks that told time by the regulated drip of water into calibrated cylinders. Ctesibius proved that air and water, under pressure, could be controlled, that invisible forces could do mechanical work. Heron inherited that tradition, and then he asked a question no one had quite asked before. What happens when you boil water in a sealed container? The answer would be the Aeolipile, the first steam-powered device in history, and the machine the world would not be ready for until the reign of King George III. Here is exactly what Heron built. A bronze cauldron sits over a fire. Above it, mounted on two hollow tubes that act as pivots, is a sealed bronze sphere. The tubes connect the cauldron to the inside of the sphere, so steam can rise from the boiling water below and fill the chamber above. Jutting from the sphere, at opposite points on its equator, are two bent tubes. They are open to the air. When steam fills the sphere, it has nowhere to go but out through those nozzles, and the nozzles are angled. So the steam jets push the sphere in one direction, and by Newton's third law, which Heron did not know by name, but absolutely understood in practice, the sphere pushes back. It spins. It is a reaction turbine, the same principle that will power jet engines 2,000 years later. Steam pressure becomes rotary motion, continuous, mechanical, unstoppable as long as the fire burns. Heron calls it the Aeolipile, the ball of Aeolus, god of the winds. He describes it in Pneumatica, Proposition 50. The instructions are clear enough that machinists in the 19th century built working replicas from his text alone, and they spun exactly as he said they would. But here is what matters. Heron does not describe this as a prototype. He does not suggest scaling it up, attaching it to a mill or a pump. In his text, it sits between a trick jug that pours wine or water depending on which side you tip, and a mechanical bird that chirps when you pour liquid into its base. It is a marvel, a curiosity, a device to demonstrate the power of steam and to amaze an audience. And that tells you everything about why this machine went nowhere. Because the Aeolipile was not the only machine Heron built. Not even close. His books describe dozens of devices, some practical, most theatrical, all of them startlingly clever. And the pattern is the same every time. The engineering is centuries ahead. The application is a party trick. Take his most famous invention after the Aeolipile, a coin-operated vending machine. You drop a 5 drachma piece into a slot at the top. The coin lands on a small pan attached to a lever. The weight of the coin tips the lever, which opens a valve, and holy water flows into your cup. When the coin slides off the pan, the valve snaps shut. It is brilliant. It is the ancestor of every vending machine you have ever used. And Heron designed it to dispense holy water at temple entrances, so pilgrims could not steal more than they paid for. Or consider his automatic temple doors. You light a fire on the altar. The heat expands air in a hidden chamber beneath the floor. The expanding air pushes water into a bucket. The bucket gets heavier and descends, pulling ropes that turn the hinges, and the temple doors swing open by themselves, as if the gods have answered. Let the fire go out, and a counterweight pulls the bucket back up. The doors close. No priests, no hands, just heat, air pressure, and weight. He describes a wind-powered organ. A windmill turns a shaft. The shaft drives a piston pump that forces air into organ pipes. Music, powered by the wind, playing by itself. He improves Ctesibius's force pump, a double-piston design with one-way valves that can lift water to heights or shoot it in a pressurized jet for firefighting. That one actually saw use. Roman fire brigades carried them, but most of his machines did not. He builds the world's first programmable machine, a self-moving cart. Wind a rope around an axle. Attach the rope to a falling weight. As the weight drops, the axle turns, the cart rolls forward. But here is the genius. By placing pegs in specific holes on a cylindrical drum, you can make the cart turn left, turn right, pause, reverse. The pegs pull strings that shift the drive from one wheel to the other. You program its path before you release it. And then there is the automatic theater, a 10-minute play performed entirely by mechanical puppets. Figures saw wood, hammer nails, launch a ship, all driven by a single falling weight unwinding a complex sequence of strings, pegs, and pulleys. No human operator, just gears and gravity. It is astonishing. It is programmable automation, the ancestor of the Jacquard loom and the punch-card computer, and Heron uses it to stage a tiny mythological drama for wealthy patrons. Every single one of these machines worked. We know because people rebuilt them from his notes, and they did exactly what he promised. So here is the question that has haunted historians for 2,000 years. Why did none of it matter? Start with the economy. The Roman Empire runs on slave labor. Estimates vary, but at Rome's height, somewhere between 1/5 and 1/3 of the population of Italy is enslaved. In the provinces, in the mines, and the fields, the numbers are higher. If you are a Roman landowner, you do not need a machine to pump water or spin thread or grind grain. You have people, hundreds of them, in some cases. And people are cheap. A steam-powered mill does not make economic sense when human-powered labor costs you nothing but the minimum food to keep them alive. There is no incentive to mechanize. None. The empire's wealthiest men do not think like industrialists. They think like landlords. Power comes from land and the bodies that work it, not from factories or engines. So Heron's machines become temple magic. Expensive toys for the rich. Clever demonstrations of pneumatic principles for scholars. But not tools. Not engines of production. Because production does not need them. And even if the economic will had existed, the engineering would have failed. Because there is a second problem, metallurgy. Ancient bronze and iron can be forged, cast, hammered into shapes. But the precision required to contain high-pressure steam, to machine a tight piston seal or a one-way valve that does not leak, is barely within reach. The Aeolipile works because it does not need to contain pressure. It is an open system. Steam rushes in, spins the sphere, escapes into the air. There is no boiler explosion risk because there is no sealed boiler under load. But scale that up. Try to drive a piston, lift a hammer, turn a millstone, and you need pressure. High pressure, contained pressure, and the seals fail. The bronze warps. The whole machine becomes a bomb waiting to go off. When Thomas Newcomen builds the first practical steam engine in 1712, it is made possible by new boring techniques for cannons. Precision metalworking that can machine a cylinder smooth enough to seal. Heron did not have that. Neither did anyone else for another 16 centuries. So his machines stay small, low pressure, powered by falling weights, siphons, air displacement, not by contained steam under load. They are marvels of ingenuity trapped in an economy and a material science that cannot use them. And then Alexandria burns. The exact timeline is messy. The Library of Alexandria dies slowly, across multiple disasters, not in one clean bonfire. But by the time the Roman Empire collapses, the museum is gone. The workshops are gone. Heron's books survive, copied and recopied, but the tradition dies. No one builds the machines anymore. No one teaches the principles. The knowledge scatters into fragments. and steam engines disappear from the world for 1700 years. 1712. England. A blacksmith named Thomas Newcomen has a problem. Coal mines keep flooding, and the only way to pump them out is to hitch horses to a beam pump and work them in shifts until they collapse. It is slow, it is expensive, and England is running out of shallow coal. So Newcomen builds an engine. Steam pushes a piston up, cold water sprays in, the steam condenses, the vacuum pulls the piston down. The piston pulls a beam. The beam drives a pump. It is loud, inefficient, burns coal by the ton, and it works. 50 years later, James Watt improves it. He adds a separate condenser, captures the wasted heat, cuts the fuel consumption by 75%. And now steam is not just useful, it is profitable. Mines buy them. Factories buy them. The engines start driving looms, hammers, trip hammers, everything. And the Industrial Revolution begins. Not because Watt was smarter than Heron. He was not. But because he was born into a world that needed his engine and could build it. Heron had the idea. He had the working model. He proved that steam could spin a wheel. But ideas do not change the world by themselves. You need cheap energy, coal, not charcoal. You need precision metalworking. You need an economy that rewards mechanization instead of punishing it. You need 1,000 things to line up at once. Heron had one piece of the puzzle, 17 centuries early, and it sat on a shelf, a temple trick, a bronze curiosity, while the world spun on without it. So here's what the Aeolipile teaches us. Genius is not enough. A working prototype is not enough. One brilliant engineer, alone, cannot drag civilization into the future if the future is not ready to be dragged. Progress is not a spark. It is a fire. And fire needs fuel, oxygen, heat, all at once, or it goes out. If you want to know what else burned with Heron's workshop, that story is next. And it is worse than you think.